So then you looked at this one with your brains filled with long division and completing the square and substitution and hopefully inverse trig. Why were these the things rattling around in your brain? Well, because you noticed that this is not anything that's one of our patterns. So we're not going to be able to do this as an antiderivative. Okay. For those of you that are wondering what's happening, I'm doing this problem and I'm trying to present it to you in such a way as one might do if one were trying to solve this problem on their own without knowledge of how to do it, because that's kind of what we're moving into. We're moving into the phase of antiderivatives where it's not going to be like, yo, dude, we're doing substitution, use substitution. We're moving into a world now where we've got more variety of anti-differentiation. We need to prepare for that. So we look at this and then we just kind of think about it. So we think about, well, long division doesn't make sense. I'm going to give you this one for free, everybody, because this was the biggest issue I saw in the work you shared with me. A lot of you said this. That is not correct, because that is only partially correct. It's greater than or equal to. So if you learnt greater than, you need to modify your thinking right now and henceforth to say greater than or equal to. So the degree of the denominator compared to the numerator is not greater than and not equal to. So long division does not make sense here. Does completing the square make sense? Well, it might. We could definitely complete the square here. X squared plus 2x is a pretty nice one. 2 is nice and even, okay? So I personally tend to think about substitution first. So that would be my recommendation. So the question is, what would you substitute for? Do you think it makes sense to substitute for 2x minus 5? Hopefully not, because the derivative of 2x minus 5 is 2, which is not going to help with the denominator of x squared plus 2x plus 2. So that's kind of bad. Okay, how about if we substitute for x squared plus 2x plus 2? Well, that actually seems pretty decent. I mean, it's not a good match, right? Because check it out. The derivative is 2x plus 2. But it's actually not bad. So, a couple of things I'd like to mention here. First thing is, you need to make sure you're being very careful with parentheses. We haven't done a whole lot of substitution where we have binomial or trinomial terms after taking a derivative. But if you multiply both sides by dx, you are multiplying this entire right side by dx. So if you write 2x plus 2 with no parentheses, that's actually not correct. Now, it probably won't affect your work, but it is incorrect math. So be mindful of that. Okay? So substitution doesn't quite work. Okay, maybe. Let's check out completing the square. So if I'm completing the square, I would look at x squared plus 2x plus 2. Specifically, x squared plus 2x. Then I want to add and subtract to the same thing. Okay, so what's the same thing? Well, I take b, which is 2 divided by 2, and square. That's 1. So I look at x squared plus 2x plus 1. That's the part I'm factoring, which is x plus 1 quantity squared. Okay. So if I do that, how's that look for the denominator? I mean, it kind of works, right? Kind of works. The answer to the question, which one, is actually a both. We're going to use both here. So the particulars of why it's both are not really important, but because it's both, this is a problem I want to go through with you. So when I look at 2x minus 5, it's really not that good for completing the square or substitution for the limitations that were just outlined. Okay. So what I'm going to do here is a fancy bit of math that you don't really need to do a whole lot in calculus, but is definitely worth talking about. And that is, I want to add 0. Now, I don't just want to add 0 like this, because adding 0 like this doesn't help. Okay, I want to add 0 in a particular way. So those of you like, what are you talking about adding 0, Mr. Lepkowski? That's exactly what you did when you did completing the square, right? If you add 1 to subtract 1, you're adding 0. You're adding a particular type of 0 when you're completing the square, but you can add 0 anytime you want. The problem is there's infinitely many ways to add 0. Like I could add a half and subtract a half. I could subtract 5 and add 5. The question is which one works? So which adding 0 out of all of the infinite ones am I going to choose? And the one I'm going to choose is this one. I'm going to add 2 and subtract 2. Why would I choose that one, do you think? Why is that the one I'm choosing? That's what you should be pondering right now. So why is it I added the exact 0 of positive and negative 2? Why is that the one I chose? Well, I chose that one because of the substitution. The substitution says I need 2x plus 2, not 2x minus 5. Okay. So the 2x plus 2 part would be fine to substitute here, right? That would be fine if we had this. Substitution is good, yes. Substitution works perfect here. The problem is I don't have that. I have 2x plus 2 minus 7. So what am I going to do with that? Well, what I'm going to do with that is something that you have not done a whole lot in math, but we are going to be doing a fair bit over the next half week or so. And that is, we are going to take a fraction which has already gotten a common denominator, and we are going to rewrite this fraction so that it still has the common denominator, but the numerator is going to be different. So check out what I've done. I have a fraction strategically designed so that I can do substitution, and I'm taking that fraction and I'm decomposing it. So what decomposition means is breakdown, not the rotting version. That's not the one we want from science, but the idea of breaking something down, decomposition. So I'm taking a fraction that is full and composed, 2x plus 2 minus 7, that's the numerator, x squared plus 2x plus 2, and I'm decomposing it into fractions of the same denominator. You hardly ever do this in math, right? Hardly ever. What you normally do is you get a common denominator and then you combine, you compose. We're doing decomposition. We're doing the reverse of that. And we're doing the reverse of that for a very particular reason, which is I could now say I have the indefinite integral, 2x plus 2 in the numerator, x squared plus 2x plus 2 in the denominator, dx, added to negative 7 in the numerator, x squared plus 2x plus 2 in the denominator. Okay? So again, and finally, I'm not expecting you on your own to do any question this difficult. Honestly, the most important parts that I hope you paid attention to and made sense of were the first part, where I was doing some analysis and figuring out what to do. Okay, so like this first part here, I hope you paid careful attention to that. And then I hope you start paying really careful attention to everything that's about to happen with these two things. So if the adding zero thing and the whole splitting and how do you know, like that's confusing to you, that's okay. You're never gonna have to do that on your own for this class. If you were able to follow it, great. But you need to be able to follow what I'm about to do here for these two separate antiderivatives. Each of these separately from each other is fair game. You would need to do something like the left one and something like the right one on your own. So make sure you're 100% engaged, even if you're just kind of like, add zero, don't comprehend. Make sure you're locked in now. So the first one, I've already done some analysis here. Substitution is going to work out great, isn't it? Yeah, I'm going to have x squared plus 2x plus 2 du, the derivative is 2x plus 2, that quantity times dx. So this first is primed for substitution. So u is going to be right here, the denominator. Du is going to be the 2x plus 2, that quantity times dx. So after substituting, I have 1 divided by u du. And that means I have the natural log of the absolute value of u. There's going to be a plus c, of course, because this is an indefinite integral. And because I substituted for x, my final answer is going to be the x squared plus 2x plus 2 plus c. Okay? So this first problem right here, you need to know how to do. Start to finish with a plus c, okay? You got to be able to do that one. It just so happens I was trying to be extra fancy and put everything into one problem. Okay, this other one, the -7 over x squared plus 2x plus 2, you have to be able to do that too, separate from this one. Okay, so how'd you do that one? Well, we can complete the square here. And if we complete the square, we have the antiderivative of -7. I've already done this. It's x plus 1 quantity squared plus 1. What is the antiderivative here? X plus 1 quantity squared plus 1. That's an arctangent. First time we've done one of these together. So it's arctangent x plus 1 over 1 times 1 over 1. So remember, a is the squared constant. And when you're doing the arctangent pattern, it's 1 divided by a times the arctangent of whatever your x is, your variable expression, divided by a plus c. So 1 squared is 1. That's why a is 1. But there's also this -7. So I'm multiplying by -7. So -7 times 1 is -7 arctangent x plus 1 plus c. What a way to start a day of calculus. I'm going to pause recording here. So integration by parts. There's a formula you're going to need to learn, and almost always it's looking at products. So let's think about what we know about products. We know there is not a product rule for antiderivatives. We know that there is a product rule for derivatives. And we know that antiderivatives are the functions whose equation, I'll use equation, you start with. Okay, so that's what we know. We know there's no product rule for anti-differentiation or integration. We know there is a product rule for derivatives, and we know that when we're talking about antiderivatives, whatever it is we come up with, that function's derivative, that's the function that we start with. So let's go back to the product rule for derivatives. So we're going way, way back. So think about how hard the product rule was when you learned it for derivatives, and now you're just kind of like, that's in my back pocket, I don't have to think about it. So like, let's say I have some function y, which is f times g, y prime, or dy dx, doesn't matter. I'll go dy dx, I think. That's gonna equal, in some order, f prime times g plus f times g prime. Right, we remember that? Product rule, perfection. I'm gonna recharacterize the notation here a little bit. So instead of doing f and g, we're gonna do u and v. That's because the formula for integration by parts uses u and v instead of f and g, okay? That's why. So f prime would be u prime, or du dx. G is v, f is u. Make my v less like a u, sorry. G prime is dv dx. So we have dy dx equals du dx times v plus u times dv dx. So I made a notation switch. We're okay with that? Yes, notation switch is fine. All right, so I am going to say that we are going to multiply both sides by dx. So if you're curious about why we're multiplying both sides by dx, that's because it works. But we have a specific formula in mind. That's why I'm doing it. So I have du times v. We actually write it as v du plus u dv. Right, you follow that? Okay, multiply through, we get that. So before I finish, I just want to go back and remind you, we start off with a function that is a product, and we need to go backwards following the product rule in order to come up with the function whose derivative is this product here. That's what we're trying to do. So that's why this formula feels contrived and cumbersome. All right. That's why the formula feels contrived and cumbersome. Because we have a specific goal in mind. We are going to do the antiderivative on both sides. So we have y equals the antiderivative of v du plus the antiderivative of u dv. A little bit of substitution, so everything is in terms of u and v. Namely, remember y is u times v. And last but not least, a final arrangement. Final arrangement of terms. Oh, I'm getting odd. Sorry. Computer errors. Okay. So we have a predetermined outcome. Our predetermined outcome is we want to have u dv by itself. So I subtract v du from both sides. And then typically we write it in the other order. Namely, the thing that we want u dv on the left side. So this right here, this is the formula. That, if we follow, we're going to get a function when we take the derivative that gives us the original. So, not to belabor the point, because it's a formula, the trick with working with a formula is, first of all, knowing what the quantities are, and second of all, figuring out how what you have fits into that formula. So, why do we have integration by parts? Well, because there's functions like this one, x times the cosine of x dx. And x times the cosine of x dx is not on our list of antiderivatives, right? X cosine of x is not on there. It is not going to work with substitution, right? The derivative of x is not helpful. Cosine of x, the derivative is negative sine of x. That's not going to help here. I don't have a sine of x anywhere. So I need something else. And that something else is going to be integration by parts. So if you're memorizing formula, regardless of the class, it is best to make your first move to always be recopying that formula. So I'm going to recopy the formula. And this is where the parts come in. I need to figure out for x, is x u or is x dv? I need to figure out, is cosine of x u or is cosine of x dv? This is what it means by parts. I've got two things here in my product. I got to figure out which part goes with which. And the answer to that question is whichever one of these is going to simplify the integral. What do I mean by that? Well, if I let x equal u or u equal x, if I look at my formula, I need a du. Okay. If I were to let x equal dv, I need v. So that means I need an antiderivative here. So let me ask you this. Which one of these simplifies the integral if I pick it? Is it simplified to take the derivative of x to get 1? Or is it simplified to take the antiderivative of x to get 1/2 x squared? Which one seems simpler to you? I think you'd agree letting u equal x, yeah? Yeah. So that means if u is x, dv is cosine of x dx. So we anti-differentiate dv, we get v, Anti-differentiate cosine, we get sine of x, and we can actually make our formula work now. So the antiderivative of x cosine of x dx equals u times v, which is x times sine of x, minus the antiderivative of v, which is sine of x, du, which is dx. Oops, I wrote this wrong back here, sorry, dx. Okay. Antiderivative of sine is negative cosine. So we have x sine of x plus cosine of x plus c. This is the function whose derivative is x cosine of x. Okay. I know this is true because I can differentiate. So I need the product rule here. Okay, derivative of x is 1, so I have a sine of x plus derivative of sine of x is cosine of x, so that's x times cosine of x minus sine of x. Oops, that should have been a 0, sorry. Plus 0. And these two guys right here, they zero themselves out, and we have x cosine of x, which is what we were after from the beginning. Okie dokie. That was a very quick bit of work looking at integration by parts.